Hello, everyone. Before I start, I just want to say thanks to the organizers for setting up this nice workshop. And I will talk about large baseline optical imaging assisted by single photons and linear quantum optics. This is my most recent piece of research, which have been carried out in Sheffield with Peter Koch. And I want to say also thanks to these two people, Zijin and Cosmo, because we had like a nice and helpful conversation, and for their feedback as well. So, okay, this is the outline of the talk. I will start by giving some motivations behind this work and a little bit of background. And I will then discuss a little bit of imaging, but in terms of a metrology problem. After that, I will introduce the setup we used for our study, for the work, which basically is a system is a large baseline telescopes that employs just single photon sources. And eventually I will present you some of the results we got. So, okay. Oh, no? Okay, sorry. Okay, the general goal for telescopes is to improve the imaging resolution. So how do you define the imaging resolution? In general, this is defined in terms of the resolving power. Why does it go? Sorry for that. Okay, so the imaging resolution is given in terms of the resolving power of your imaging apparatus. And this is defined as the ability of distinguishing 2-point sources as two distinct objects. So in general, this is given as a minimum, you can quantify it as the minimum resolvable angle between two sources. And there are many quantitative criteria. One of these is the Rayleigh criterion, that, sorry, just a second. Okay, never mind. Which basically says the aperture size of your imaging system, which says that the minimum resolvable angle is given in terms of the wavelength of your resource, lambda, and the aperture size of your imaging system. So the larger is the aperture size of your system, the smaller is this angle, the better you can distinguish 2-point sources as two distinct objects. And this means that your image resolution goes like 1/L, and at the end you will get better images if the aperture size of your imaging apparatus is larger. So there are different techniques that have been employed in astronomy for increasing this aperture size. And interferometric telescopes are one of them that are already well established. So this basically consists in combining together different telescopes to form a single imaging apparatus whose aperture size is larger than each individual ones. So here, for example, we have two telescopes A and B placed at a distant cell, and they will collect some light coming from a distant star source that will reach your receivers with a certain angle theta. Then you collect this light, and you have to let the light to interfere. So basically, you have to recombine the light through some mirrors, beam splitter, and then perform your measurement. So the thing is that the light will reach the telescope with the two telescopes with a certain angle theta. And we see that at one side of these telescopes, there will be an extra length that the light has to go. So this will give rise basically to some relative phase shift, phi, which is proportional also to the length, to the distance between the two receivers. And through this relative phase shift, we're able to get information on the star position, because this also depends on theta, and theta is the geometrical angle at which we we receive the light. So it will carry information about the position of the star compared to the baseline of your apparatus. With interferometric telescopes, so then the aperture size of your imaging system is the baseline, and you can create very large baseline with these things. So this means you can get a very highly resolved images. And the most successful example is the first ever image of the black hole, which basically it was taken by combining different telescopes into a single apparatus whose aperture size was almost the diameter of the Earth. So there is a little bit, there are some differences when we talk about optical frequencies, because optical frequencies are very high, and this means that you can't actually detect, you want to measure the relative phase shift, but you cannot do that in a direct way with optical frequencies because electronics is too slow. So, and also you have to bring together the signal physically to make it to interfere. So, of course, if the baseline is long, and this is one of the main things we are saying, you will encounter a lot of problems, like, for example, phase fluctuations, photon loss, because you have to transport your photon coming from the star to one receiver or the other, like to perform the measurement. All of these things set very strong limits to the baseline. But there are some solutions that has been proposed that employs, for example, quantum information technology. And I will mention just two of these. So one was suggested by this very recent paper, where they employ quantum memories and error correction to prevent the photon to protect the photon from the transmission loss. But this, of course, requires like a little bit of advancement in the technology. So what we propose here is another setup that relies just on the use of a single photon source. So you place between the two telescopes a source that generates a photon, and you can generate this photon in a number entangled state. You send it to both receivers, and then you perform two measurements above the receiver sides. This will, of course, has the advantage that you don't have to transport physically your photon coming from the star, which is like precious. But you can use an extra photon from the lab that you can generate. So now we want to talk about imaging in terms of metrology. So we want to rephrase this problem as a parameter estimation problem for our relative phase shift phi. And the error connected to these parameters is lower bounded by the Fisher information. And the Fisher information is given in terms of probability of obtaining some outcome J, which in this case correspond to a specific distribution of your photons across the detectors. So in the simplest case, you have two photons, and you can have these photons detected in the four different detectors. So let's give this simple example. So we have one photon coming from the star, one photon that is the ground-based one. The star photon is assumed to be in a thermal state, and we see that the phase shift enters this state here. The ground-based photon can be just simply be a number entangled state. So now the information is encoded in the correlation between the two receivers, A and B. So when you compute the probabilities, you have different situations, right? So you can end up, both of your photons can end up on one side of the receiver. And in this case, you will not get any information on your signal. So only four outcomes actually will give you some probabilities that depend on the relative phase shift phi. And all the other probability distribution will bring you no information on the signal itself. So this results in a Fisher information which is just 1/2. And it means we have half of the information, and And also, we're not even taking into account photon losses, because when you have to transmit these photons and you have to use fibers, so you will have to take into account large photon losses. So what we proposed here, it's telescopes that use these single photon sources, but more than one. So we have n sources, places in between of the two telescopes, and increasing the number of sources means that you will bring more contribution to the correlations between the two detectors, and therefore more contribution to the probabilities, and this might give you an enhancement of the Fisher information, so a better estimation of your relative phase shift and better imaging at the end. So in this setup, we have single photons that are in a superposition of going to each side of your receivers, A and B, and then you have to do. So in the simplest case scenario, we were having a beam splitter just to make the interferometric measurement. Here we can implement like a quantum Fourier transform that will mix your ground-based photons with the photon coming from the star. And we are assuming that at the end you have photon count detectors with a very high efficiency. And the photon coming from the star is assumed to be in a thermal state with a low emission rate, epsilon. So in an ideal scenario, when we increase this number of sources, this is what happened to the Fisher information. So we go from 2 photons, so one from the star, one from the base, up to 5, and we see that there is an increment in the Fisher. So this is actually good and solved the first problem we were saying. So we are gaining a little bit more information from increasing the correlations between the two receivers. However, we have to still take into account the photon losses. To model losses, we use we inserted beam splitter in the transmission line. And we can just say that there is a transmittivity factor that depends on the distance. So L is the distance between the receivers, and the fiber attenuation length, L0, which is of the order of 10 kilometers or something. So now you are in a situation where you have n number of photons, but only one comes from the star. You can lose some of them in case the number of photons you might lose. So the number of detected photons now is not n anymore, but it's d. So you have n different scenarios. You can lose 1 photon, you can lose 2 photons, and so on. Each of them will come with different configurations that can be distributed. The photons can be distributed across the detectors. So the Fisher information is a little bit more complicated now, and it has to, the sum has to run over all the possible configuration for the possible cases. But we proved that we can actually rewrite the Fisher information in a simpler way. So just as a sum of contribution of Fisher information for partial detection. So FD is actually the Fisher for a number d of detected photons, which is smaller than n, the total number of photons. And QD is a probability of detecting the photons, which can just be expressed in terms of the probability of losing only 1 photon. And so there are some problems that needs to be addressed. So we said, okay, we are increasing the number of photons because we want more coherence. However, the more photons we have, the more losses we have. So, and still, the star doesn't always emits a photon. So if the emission rate is very low, this might significantly impact the Fisher information. When we have to take into account the star emission rate epsilon, we can say just that the initial state is this density matrix here, where the first part is just the scenario in which the star does not emit a photon, so it's just the vacuum state, plus psi1, which is the thermal state we saw before, so it contains the information about the relative phase shift. And now the probability distribution, the total one, is just the sum of two contributions that correspond to the possible scenario, because you're not able to distinguish when you detect when you detected d photons. You don't know if you lost one in the transmission or if your star didn't emit it at all. So at the end, you will get this coefficient here in the Fisher information that depends on the star emission rate. And if this rate is really small, this might significantly lower your Fisher information. So can we get an improvement, actually, by increasing the number of photons? If the Fisher scales like quadratically with epsilon, then for sure you will not, because you will get a very deteriorated metrology protocol. So at the end, your error is going to be too large. However, if your Fisher scales linearly with a epsilon factor, then yes. And these are some of the results. So of course, the Fisher scales linearly. This is the Fisher information for different values of photons, ground-based photons, in function of the emission rate. And we see that it scales linearly with it. And the more you increase the number of photons, the higher is the values of Fisher. So the smaller is going to be the error on your parameter. So we can say that when we increase the number of photons, basically, yes, we are increasing loss. And we don't know which photon we are losing on the transmission. However, this lack of knowledge is compensated by the fact that we are creating more coherence between the two receivers. So there are two effects now that have kind of to be balanced. On one side, we are increasing the loss. On the other side, we are also increasing coherence, which is good. So at the end, there is a trade-off between these two effects, which will lead to an optimal distance between the two receivers, and then to an optimal resolution. The resolution can be defined in terms of the relative phase shift, which we saw before. So we have phi that for small angles can be just approximated to KL theta. We know that the error, the variance for the relative phase shift is lower bounded by the Fisher information. So by combining these things together, we get that the minimum resolvable angle is given by this expression here. So it depends on the length L, which is the distance between the two receivers, and the Fisher information. So the higher these two quantities, the smaller is your resolution, the better is your imaging. And this is the plot of the resolution in terms of units of fiber attenuation length. So there is this minimum here is the optimal resolution, which is obtained to a certain values alpha. And you see that the higher, the more number of photons we have, the smaller is this angle, so the better is your resolution. And this minimum is like shifting a little bit to larger and larger distance, which means like that the optimal distance, so for which we obtain the best resolution, is actually increasing with increasing the number of photons. So in this table, there are some values for different numbers of photons, and we see that we go from 2 photons, where we get a resolution of 19 microarcoseconds, to up to 5 photons, where we get a resolution of 10 microarcoseconds. And we see that the optimal distance at which we obtain this actually increases. So when we increase the increased optimal resolution, we also have better imaging resolution. And So yes, in conclusion, just to sum up, I presented you like this protocol for photon-assisted imaging in presence of like very large photon losses that works for large baseline telescopes. We managed to extend the baseline, therefore we managed to get an enhancement in the resolution of imaging for positioning of point sources. And another thing I want to stress is that the only elements we used here, they are very, very simple technology like currently available. So single photon sources, optical fibers, or linear optical circuits. So all these things can actually be done in an experiment without using quantum memories or repeaters, which might be a little bit more demanding. So with this, I conclude. I thank you all for your attention.